Hello, hello, and welcome to day 2 of Python for Scientific Computing, edition 2025. I hope day 1 was exciting. I understand that it might have been overwhelming for some of you, but we try to give you as much as we can in 3 days, and then later you can rewatch the recordings, go through the Python code examples. But today with me here, we start with some icebreakers. We have Simo and Thomas from Aalto University. Simo, do you want to say briefly something about yourself?
Yeah, hello. So my name is Simo Tuomisto. I'm a research software engineer in the Aalto Scientific Computing. I've been part of teaching this course for as long as the course has basically been here. So back in the olden days. But yeah, so we'll be talking about a lot of subjects today, and I'm a seasoned Python. Like yesterday, there was a question of what languages we're using. Like my first summer job was converting Python numeric to NumPy, so it's like
That's
back in the,
nice.
yeah, long history with NumPy, so it's good, and Python, so it's good to follow up or keep going with that.
And then with us today is also Thomas. Do you want to mention something about yourself, although you were already
Yeah,
on
but I didn't
stage
actually
yesterday?
introduce myself yesterday. So
That's
I'm
good.
also a research software engineer at Data Scientific Computing. Um, been teaching here now also for the last 4 years or so. Um, I'm originally from a bioinformatics background, so using MATLAB very, very way back, or actually started with Java. So Python only came later in my in my career, but yeah, nowadays, since a lot of things are working in Python, I'm also doing stuff in there and doing quite a lot of actually web development things. So more TypeScript, JavaScript,
Yeah.
but backend stuff in Python.
So Thomas is sharing the screen now, and Thomas is showing this notes document. You all have received a reminder from me via email from the link of this notes document. And there I wrote a couple of icebreakers that I'm going to ask to our instructors of the day, especially the one, how do you make figures for reports or articles, or even in general, maybe even figures, let's say that today for the teaching materials, you need to make a figure. So I start with Simo. How do you usually make figures or plots?
Yeah, that's a good question. Like I often do use different kinds of tools. So back in the day, I used to use Matplotlib a lot. Nowadays, it's much more like Vega Altair that we'll be talking about today. But of course, there's like other mentions there, like ggplot2. I've been using that as well, and other tools that are better for like diagrams and teaching stuff. So yeah, just yesterday I made like a change to the material, and I used GeoGebra to create one figure, and sometimes I use this graph tool called YEdit. YEdit. I don't know how to pronounce it, but YEd, which makes it easy to create diagrams and UML diagrams and that sort of stuff. There's also this XCaliDraw that is nowadays like really nice if you want to do a quick, dirty figure, so you can demonstrate something for people
Nice.
in the web. But
I
there's plenty of tools.
Yeah, I know less than half of the tools you mentioned, so if you can please add them to the list there. That.
Yeah.
And what about you, Thomas? Which
Well,
tools do you use?
when I still used to actually create scientific plots and things, it was mostly at the time in MATLAB itself. So just the MATLAB plotting things. Um, Nowadays, I'm mostly doing diagrams and things with partly Draw.io, sometimes Inkscape if stuff needs to be, if I need to have a bit more control over details and things. Um, and actually rarely do these kind of standard plots anymore.
Yeah. Have you, when you were making plots for papers and things like that, did you try to make everything as much as possible with the code, basically with the plot, or did you and your colleagues maybe, after the initial plot, lots of whatever, Illustrator or Inkscape or Photoshop or?
I try to avoid post-processing figures as much as possible because it only messes things up and the figure actually gets less usable. At the same time, I try to normally just provide the raw data for whatever figure I created anyways, so that people don't need to extract data from figures, which is, in my opinion, really, really painful to do.
Yeah. What about you, Simo? Do you try to avoid these manual tools? Although I believe
Yeah.
some of the tools you mentioned earlier, some of them are just
Yeah.
manual in a sense that you draw with the
Yeah.
mouse.
Yeah, because like there's like I would say there's two kinds of diagrams. There's diagrams that are like figures that you want to create to illustrate a point or an idea, and they are not necessarily published, but they are like tools for aiding discussion and that sort of stuff, like the diagrams of how your program works or diagrams of like, what's going to happen with the data or whatever, like creating like flowcharts and stuff like that. And that's never going to be published because it's just something you use to refine your ideas. And for those things, like what you see is what you get kind of tools are very nice, because then you can just like drag and drop stuff and it doesn't matter if it looks nice because it's never going to be in a paper or something. And when you get to the like point where you want to actually like have something that is publishable ready or whatever, then you need usually to just pick one tool that you can programmatically create the stuff, and then like tune everything. Like then it becomes like a hell of micro tuning, where you tune every small bit and everything. But that's not feasible if you try to like create a quick demonstration or quick graph for somebody
Yeah.
else. So there's like use cases for both kinds of tools.
Final
Completely agree
question
with that.
for both of you. Do you always label your axis, or do you forget sometimes to label the axis?
I would answer it a similar way as what Simo said about the building your figures. If it's something for a quick sketch for some internal presentation or things where you just want to show what's the general situation, yeah, can happen very, very often that there is a missing axis label or something. For papers, I think for the stuff that I published, I had all axes labeled. I
You
hope
better.
so at least. I hope so at least. Um, but yeah, for internal preview things, just so yeah, can
Yeah,
happen.
I was quoting this XKCD. I added the link there that, some people, I'm very strict. If I see a paper that doesn't have labels on the axis, I will reject if I'm the reviewer of that paper.
And
All
you're
right.
right. You're absolutely right about that.
Yeah.
All right. So it's almost o'clock. Let me check the exact number of seconds. So 15 seconds still, and it's great that people are already editing the document. And basically, we can actually start. So maybe if you zoom a bit into this, yeah. Hello, everybody, and welcome to day 2 of Python for Scientific Computing. Yesterday, we had a look kind of how to run Python, for example, using Jupyter, and what's under the hood when it comes about loading data. So we talked about NumPy and Pandas and Xarray. Today we continue with the more kind of data science workflow, like for example, plotting the data, and more in general, we will also cover a little bit more with working the data. In the afternoon, we go a little bit more advanced, maybe if you want to think it like that, meaning that we try to remove the human from the interface, that we can actually run Python without clicking cells on Jupyter, and basically that means scripting, and scripts are very useful for many different things, especially when you move your Python code and data to larger system like high performance computing clusters. And so that will be very interested. So again, there will be a little bit for those of you who are starting, but also something interesting and useful for those of you who have been using Python for many years. Now, just a reminder, we use this, what's the name? Collaborative notes document. So Thomas, if you could switch to the collaborative notes. And so if you scroll, at the very top, there is this pencil that Thomas is clicking. And so when you click the pencil, you switch to this edit mode. And so, for example, here, Thomas could answer one of these icebreakers on, okay, he used to use MATLAB and Inkscape for making figures. And so you can do the same. You can already test this. They are able to edit it and answer your questions. A little bit more above from today's, I left the feedback from yesterday. So if you were around yesterday and you didn't have time to write some feedback from yesterday's episode, you can still add it at the top of this notes document. What else? The videos from yesterday are already available in our TwitchTV channel, basically the same TwitchTV link that you're using today. And at the end of the week, we will upload the videos to our YouTube channel so that you can watch them again and again and again. But now maybe Thomas can also show how to go back to the view mode, because there's many hundreds of people editing in parallel and our poor server sometimes needs a rest. So when you click on the eye icon, it goes back to this view mode. But maybe one last reminder that if you use Twitch TV, remember to set the quality of the stream to source. Otherwise, Twitch TV will pixelate the image, and it's not nice when you're looking at text or code. But basically, after this very short intro, I will leave the stage to Simo and Thomas. And so enjoy your morning with Python and talk to you later.
Yes. So hello. And before going to the plotting, let's talk quickly a recap, like previously in the previous episode, what we did yesterday. So yesterday, the question was, okay, an introduction to the NumPy ecosystem as a whole, and there was a lot of stuff there. Like for many people, it's probably first introduction to Python in general, or scientific Python. So there was a lot of stuff. But so a quick recap before we start the plotting, because it's important to remember where we came from and how we utilize those tools now for new things. So first off, NumPy. So the idea behind NumPy was we take, instead of using like the Python basic types like integers and numbers, we use arrays. So we collect a lot of these numbers into one big block. So then we can do like collective operations on these numbers. So, and we can calculate sums for a huge number of numbers at a time, or we can calculate various like additions or multiplications or whatever over a large number of data all at once, which brings speed back into the question. So that's basically the idea of NumPy. And NumPy is underneath all of the like Python scientific computing, like everything in scientific computing is like built upon NumPy and the NumPy API. So because NumPy provides these kind of like basic tools of like, okay, here's an idea of lots of numbers and that have a certain data type, and we can do some collective operation on them. Then we can build other tools on top of this. So one of these tools was Pandas that we went through. So Pandas was a tool and library and framework for working with lots of these arrays organized into this data frame. And in the data frame, we had lots of these arrays as columns. So each column was one array. And we had this representation of like this tidy data representation where each column is a variable and each row is an observation. And because now we had this kind of like mental model or organization for our data, we could have like lots of data organized into one data frame instead of like figuring out individual arrays. We had lots of these. We had lots of these collected into one data frame, and then we could search in the data frame and do all sorts of operations with these columns. Then we had the question of an X array, which was, okay, like what if your data isn't just one-dimensional array, but you still want to collect them together somewhere? So that was the idea of X array, that we had multi-dimensional data, like a grid or something, like a multi-dimensional grid, and we put that into X-array data set. So we collect all of that together into this kind of like a collection, so that we can then do operations on those and keep our like sanity when we have to operate with lots of different data, and try to want to figure out certain subset of the data that we want to operate on. So basically, it's all like NumPy as at the bottom is the kind of like workhorse that speeds the things up, and pandas is a way of speeding our like work up. So it's a way of making our data organization and like make it easier to create workflows and create code that makes us able to answer questions like with that data. Instead of like having million arrays floating around, we collect everything into the data frame. And X-array does the same kind of thing, but for multi-dimensional data. So basically, this was the whole day here in 5 minutes. But of course, there's lots here which is like
Skipped over.
skipped. But basically, that's the basic idea. And the basic idea is that like why does this matter? Like why can't I do whatever I want to do? Like the reason is that if you have because there is this NumPy ecosystem, like every other package and every other framework can build upon the like chosen types or built upon the way that the previous ones did, like previous packages did. So they can reuse the same ideas, and they can add more functionality that you can achieve. And that only works if there's like a common truth or common like standards. And NumPy is basically the standard for Python. Like that is the standard for how to represent numbers and data in like close to the machine level speed, like so that you don't like run stuff slowly. And pandas is a way of representing this kind of like tabular data, and that is basically a standard. There's like extensions or other packages that do similar stuff to pandas, but basically pandas and data frame is the kind of like standard for organizing this kind of like tabular data. So basically, here's where we can jump into the plotting. So because like why? Okay, what does this matter? Like the reason is that when we use now plotting, we want to plot stuff. We can do it with multiple ways, but the tool we are going to be talking about, the Vega Altair, is a tool that builds upon pandas, like or the structure that pandas provides, and it can do lots of beautiful plots very easily because it knows that okay, like stuff is in data frames. But there's of course other plotting tools that we're skipping over. So one of the biggest is matplotlib. So that's basically originally started as MATLAB's like plotting interface made into Python, because like NumPy is heavily influenced by MATLAB. Like the underlying thing is heavily, back in the day at least, it was heavily influenced by MATLAB. So then they wanted to do a plotting library that was similar to MATLAB, and that's Matplotlib, which is a great plotting library, and it's used widely, and it's very good thing to use. But it's not well, it has its own complications. But there are previous lessons in this course, previous years, that you can find in in our YouTube channel that you can check if you want to like have a good lesson on it, and you can check the materials. But we are going to be focusing on Vega Altair this lesson, and Vega Altair is a library that is more heavily influenced by ggplot, which is a library from our ecosystem, which is this kind of like declarative plotting. There are many other like plotting tools mentioned here, so there's no like also already mentioned in the icebreaker. There's lots of tools. None of them are wrong if you get good plots out of them. But Vega Altair plays nicely with the data frame. So like if you have your data in this kind of like format that Pandas provides, so stuff is in columns, like you have columns of data, each your data is in columns, and each row is an observation. Then Vega Altair can read this in and make easy, beautiful pictures with minimal amount of code, and with this kind of like declarative language, so that you can like you don't have to wonder why certain things look the way they are. Like you don't have to like figure out, okay, what is this access I need to modify or whatever it is. These kind of like low level details of the library. So that's basically the gist that we are going to go through today. So if we should we just start doing examples
I would add just one thing that's mentioned here as well, and why we are doing the plotting in libraries and stuff at all, and not just use some GUI interface to draw lines like Excel or stuff. What we want to have is a script that reproduces the figure, because that's also part of reproducibility. Because then we have a clear view how the final plot relates to our actual data, what is what, where does the data come from. And we want to have as little post-processing of these plots as possible, because if you do post-processing of a plot, it's so easy that something gets slightly moved and you don't even notice it at first, and it messes up the whole, this is the actual data that is being plotted here. So we want to have something where we can click and this produces the plot from the raw data, and you can check, okay, what went where, and you can understand what is happening. And I think that's an important reason why we actually use all these plotting libraries.
Yeah, that's an excellent point. Like a very, very good point. My main reason is that I don't want to like figure out how to make good plots if somebody else has created or maybe a better way of doing it. But that's a more ethical way of looking at the thing. Okay, so let's start with Vega Altair, and let's start like plotting some things. But before we can start plotting anything, we need data. So in this example, maybe Thomas, can you make the Jupyter a bit bigger? The text, yes, nice. So in this example, we'll use this temperature data set from wherever. I don't know.
Tromsø, and
yeah.
I think it is Oslo, yeah.
Yeah. So like I don't know where the data is collected, but it doesn't really matter. It shows like data from different stations, weather stations, and temperatures for each month. So we have this sort of a data frame that we have over here. Like usually when we have this sort of a data, like yesterday there was already like talk about like what sort of modifications you want to do to a data when you get it. And in this case, the date is in a weird format, so it's not an actual like date. And
it's a month year date format.
So it's just a string at this point, but we want to make it into an actual like date. So like all of the columns can have data in a certain data type, and we have a data type for dates, which is date time in Python. So if we use this date time, we can then like tell that, okay, like this is now a date. So we can strip out the date from the bad string date time and then make it into an actual date that we store in a new column. So now we can start the actual plotting. So let's run this plotting code, and I'll then explain what each of these pieces mean. Do you want to, Thomas, close the Jupyter news at the bottom? It's driving me crazy.
Sorry.
Yeah, no problem. So, okay, what we have here. So if you want to show the code at the top screen. Yeah. Yes. And then we have and plot in the bottom. So yeah. So then we here have now a nice plot. Like what happened? Like what did we do to create this? And let's go through the whole thing. What Altair does. So Vega Altair is like you import it usually with this import Altair as alt. So because nobody wants to write Altair over and over again. So many packages, when you import them, they have like a preferential, like small alias that you use to use them. For Altair, it's usually called alt. So if you see a documentation or whatever, it's usually like alt something. And then we need to take the data and give it to the plotting library. And this in Altair, this works with this chart object. So everything is chart in Altair. And chart basically defines all the pieces of your plot. And when we create a new chart, the first thing we do is that we give it the data that it needs to operate on. So in this case, we just give it the data frame. And it usually expects the data to be in this data frame format. It can also accept like CSV files or JSONs or whatever, but usually what you want to do is to give it a data frame. After that, we have this mark bar. So when we have a chart, we want to modify that, and we do it by calling an attribute of that chart, and then we can specify these. We can specify how do we want to plot our stuff, and this is called these markings. So for bar charts, this is called mark bar. There are also like mark point and mark line and all sorts of like different markings that we can use to represent different kinds of data. But we tell it like, okay, how do we want to represent the data in the plot? So we declare like we want a bar chart over here. And then comes the important part, which is this encode, which sounds weird. It might remind you of like text encodings or something, but it's not that. The thing with the encode is that when we have an encoding, we convert, basically say to the library that, hey, in the chart, this thing in the data should represent this this thing in the chart. Like this thing in the data should represent this thing in the chart. And this is done via these channels, these visual channels. So in this plot, for example, if you, Thomas, want to keep it there. So we have the X, Y, and color there mentioned. So these are basically like we say that X channel, so X direction. So this is the visual channel for the X direction. We want to put the date here, like use date to represent X direction. And then for the Y channel, we say that, hey, let's put the precipitation to the Y channel, so represent that in the Y direction. But there's other channels as well. There's huge amounts of different channels that we can do in Vega Altair. So here we use color. So we just put the name to the color, and Vega Altair will automatically be like, okay, I will now colorize based on the name column of the data. And because the data is in these columns, Vega Altair, for example, if you look at the x-axis, we have these dates over there. It's no longer like in this kind of like datetime look of the data. It's actually represented as text, because Vega Altair, based on the column type, it can now know that, okay, I will want to represent this as months, month names, the x-axis range. It will automatically know that the user wants to get this sort of like representation. If it would be like nominal data, like names, like strings or something like that, it would know that, okay, I will represent this as just like different categories. Or if it would be like a continuous data, it would know that, okay, I will represent this as a continuous x-axis. So it will determine what is the channel, like how do it best represents a channel based on the data type of that channel, or that like column over there. So and let's if we look at the bit below, we can check the next plot which illustrates this this further. So if we go and do the next plot, so over here we do a new plot where we now we set the x-axis to be this year month, and then we have this column and t, and the t here again tells that it's a temporal data, but then we call it this year month, so we can say that, okay, like give me year and a month over here, and use that representation. We will talk a little about transforms later, but it's basically a transform where we say that, hey, like make the data into years and months, and put those into the X categories. When with the column after that in the channel name, we can describe what is the data type of this, like this channel. Like what is the data, like how do we want to represent it? Often like Altair recognizes this automatically, but you can all like override them if you have something that is like it's like floating point numbers, but you want to represent this as integers or something. And these channels are quite common in like statistical languages, like so quantitative, it's basically like it's categories, so it's like strings or something like that. Ordinal is like these numbers that are increasing in order, so like from the scale of 1 to 5, how likely are you going to recommend this course to your friend? Like that sort of like ordinal data. Nominal data is sorry, I misspoke. Quantitative is
numbers.
like a continuous data. Yeah, my mistake. Quantitative is continuous number data, and nominal data is something with naming. Like this is statistics talk. Like if you have ever used like SPSS or other these kind of like things, they use these categories a lot. Then there's temporal data, which is, well, time. And then there's the GeoJSON, which is like if you have a shape, like there's other things you can represent. But that's like for geoinformatics people. There's lots of support for these sorts of like special things in Vega Altair as well. But this basically tells how do we want to view in the channel, like how do we want to encode the data into the channel, like how do we want to represent it in the visual channel. So basically the whole idea is that we switch around these channels, and we put our data we put our data into the chart. Then we decide, okay, how do we want to view, what sort of plot do we want to create with the mark statement, and then we play around with the channels to well, get the kind of plot we want to do. So let's try another kind of plot. Let's add another column. So instead of doing like sub figure or something like that, or adding figure, we can just add a new channel for column. And now Vega Altair will automatically know that, okay, you want 2 columns of plots, and let's put the data from name, like separate it based on the name category. So in this case, the name was the name of the station. So we get 2 plots, one for each station. So you can also use this as a row for if you want to do multiple rows of plots. And it basically what Vega Altair under the hood does is that it does group bys. So it because the data is a data frame, it will group the data based on the value of the like in this case the column name, and it will then, like for each of those data, it will do a separate plot. We can then do, like, if we want to, we didn't like that, like we didn't want to like use so much space in our figure, we can also do something like X offset, which basically like makes all of the bars like offset from each other. So this is like common way of doing plots as well. So we can get like different
essentially bars side by side instead of
yeah.
on top of each other.
Yeah. And we can also do like in the next example, we can for example plot ranges.
I
So
think
here,
the just as I mentioned, the X offset is particularly important if you have more than 2 things. With 2,
yeah,
it's commonly not that big of an issue because you see the higher bar, you always see it in the back, but you could end up with something with not seeing something, and X offset essentially allows you to have them side by side.
yeah. And then we can do all sorts of plotting, like we can plot areas. So in the example, we can tell that we want to plot an area with X and Y, like if you go a bit down in the page,
Sorry.
yeah, like if you look at the code for that. Yes, so we can do stuff like plot areas. So here we mark areas, and for the area we want to have like an X and Y, like X ranges or Y ranges. So for that we can use this Y2. So in this case we encode, we have still the x-axis is the same, but now we highlight an area with like maximum temperature and minimum temperature. So we have 2 different columns that define these like top and bottom of the area, and where they overlap we can see this shaded region. So we can create plots such as this quite easily. And
to ensure
yeah,
that it's not canceling each other out, you have this opacity,
yeah,
which if we set this to
yeah, it's going to be,
you wouldn't
yeah.
see where except for this tiny bit here, you wouldn't see where things are. So
Yes. So there are many, like for the mark statements. So for the data represent, like how do we want to represent the data? There's lots of changes we can do. Like if we plot points, we can decide how big the points are and that sort of stuff. If we plot bars, we can make the bars rounded if we want. And there's a huge number of these examples of these different ways of encoding the data in the documentation. The documentation is really clear, and the examples are like super nice. So what I usually do is that if I want something, I will look at the examples and then check, okay, what are they? So there's huge number of these different ways of representing the data. And so basically, what is the core tenant here, or core idea? The core idea is that, like, if you want to plot something, like anyways, you need to plot it in like a paper. like you have a 2D paper that you want to plot something into. So your data will have some sort of like XY axis somewhere. And if you have your, like if you anyways need to have it in this sort of a like way, like you can't plot like 13 dimensional data or something. Like you can't plot like an X array. You have to take some slice of it, or you have to take like some average over it or something. So when you have this sort of like you want to plot something, if you can take your data, let's say you take your average temperatures or your um, like your like house price at a certain time or whatever, like you have different x's that you want to have. You can then, if you have it in the data frame in the tidy format, you can then easily tell a Vega Altair that, hey, here's my data, but here are all of the columns that are here. I want you to take these columns and convert those into like things in the graph. Like I want to take stuff in those columns and make it into something that is a graph. So then that's basically the whole idea. So let's play around with this. So let's have exercises. Um, let's have exercises and let's go through them so that you have enough time to like actually familiarize with the ecosystem. So first off, well, you can read the exercise over here, but try to reproduce what we have over here and check what you get out of it. And there's a good question, like should you format your data in pandas first before using Vega Altair? And usually like data pre-processing and stuff like that is a large chunk of everyday work when you're doing like scientific work. So usually you want to process it into a way where you can then tell Vega Altair to plot whatever you want it to plot. We'll talk later about how Vega Altair can also make like how you can modify the plots and how you can modify the data while you're plotting it. But yeah, usually you want to have it at least in the format, the tidy format, so that you can represent all of the different channels with different columns. But yeah, let's go to exercises, I would say. So should we return
back
at
in 10 minutes?
or maybe 15.
Okay, so
Yeah.
48 then.
Yes. Yeah. See you then. Bye. Hello again. So we are back from the exercises. So hopefully you managed to do them. We are going now for a break. So just a, like a reminder to get some steps in and get some water or coffee or whatever the beverage of your choice, and relax for a bit. You can of course do the exercises while the break is going, but after that we'll talk more about like what sort of things you can do in Vega Altair. There were good questions in the notes, but we'll put more there. Like if you encounter problems, if you figure out something nice, if you have I'll add a poll there of did you complete any of the exercises. Add to that poll, and we'll be back in 11 or 11 in Finnish time. Other times for like at the hour. We'll be back at the hour. So have a nice quick break, and then let's continue. So, hello, we're back from the break. Hopefully you managed to run some of the exercises and see what came out of them. So now we are going to be looking at various other like features and things that Vegalta can do. We'll check more fancy plots and stuff like that. In the notes there were a lot of good chatting. So first off, I will say there was a question of whether Vegalta is better than others. Not really. Like nothing is like the end result matters, right? Like if the plot is nice, if it was nice to make it, that's what matters. If you want to use something like Matplotlib, that's great as well. Like Vegalta has some extra features that Matplotlib doesn't have. Matplotlib has like lower level control that you can do, but it's all about like whether you get your plots done. And Vegalta is like designed for this kind of like data visualization when you have your data in order. So if your data is in a complete disarray, that might be also like it might be hard to get it into Vegalta. But that might be the least of the problems at that point. Yeah, there's no best tool. Like whatever floats your boat, like that's um, the thing you want to use. But I prefer Vegalta before because I feel like I'm more in control of what's happening because I tell it what I want to happen and then it does it. And if it doesn't do it, I will modify it a bit. But usually I look at the examples and choose a plot I want to use and then go forward. Yeah, so let's continue with the plottings and let's look at other things. So Thomas, if we check first, like how do we modify a plot? Like the previous plots, they were nice, but they weren't like publication nice. So often what we want to do is we want to customize the channels. And in Vegalta, like all of the channels that we specify, like by default, you give them these shorthands, or like usually you, when you start at least plotting, you give them these shorthands of what data you want to encode into a channel, like what data column you want to put into whatever feature of the plot. But at some point you want to make certain that like everything looks nice and like is organized neatly and whatever has a nice title or something. And for this, you can use these. You can use the channels directly. So what Vegalta does under the hood, that if it gets a string as a channel, it will create the channel with defaults, like sensible defaults, and it will use those. But you can create the channel objects directly. So in this example, we instead of like just using the channels as they are, we use we create the channels ourselves and we set the like reasonable titles for them. So we get better namings. So instead of having this like in the plot below, you can see that these are these auto-generated channel names like year, month, and whatever date, and they might not look pretty because they are basically taken from the data frame, like the names. So instead of using those, let's just give the channels different titles. And it's very simple how it usually works. So if you have a channel, you usually have an alt and then with a capital the channel, and that's the class of the channel that you want to use. So for example, X and Y and color and that sort of stuff. Like you can like like you don't have to be Sherlock Holmes to have a detective sense of like, okay, what would be the name of this channel. But if you're unsure, it's good to check the documentation. There's a whole list of like the channels named, and whatever channels you want to like modify, they're listed there, and you can check for each of these channel classes. There's huge number of parameters that you can like use to modify the plots. So you can change titles, you can change placements, you can change like rotations and all sorts of like stuff that you would want to use. Like you can optimize your plots in various different ways, and this makes it already like a bit nicer of a picture when like the small details are set up. But usually, like when you're still working on a plot, the most important thing is the graph itself, and then later on you like nitpick all of the small details at the edges. Like you can change the ranges of x, y axis and that sort of stuff. Like you can do all sorts of like you can set the limits, like whatever you can think. Basically, you can set them in the channels. Yeah. Was that not the correct one?
According to the axis, that should be a option.
Let me check.
Oh, dict float. Wait, no, float. This is a float.
Okay. Let me check the actual encoding. So Alt Y. So it's not a part of. It's not for Y. But it's for something else. But you need to give it a different like. Let's not figure it out on the fly probably. But you can do all sorts of stuff. But it's best to look at the reference in the guide, or check one of the examples and copy paste code from there. What usually people do. Then once you have your nice plot that you have, you can save them, of course, and it's very easy. You just call this save, and then what you get is the plot. And you can view it. Well, if you're saving it as a PNG, which is like a rasterized image, so it's like the raw image data there, you usually want to specify the pixels per inch, like what is the resolution of the image. By default, it can look a bit blurry, but often you want to save it as SVG or like as a vector format, or like to make it crisp, or be a PDF or something. And Vega Altair supports various different, like it supports SVG, PNG, and PDF outputs. So you can use all of these different outputs to create your plot. There's also like nice support in Vega Altair for web, like web things. So if you notice in the already in the plots we were doing, we had this like in the Jupyter notebook, we had this like interactive like semi-interactive things. That's because like it renders it as HTML, and it shows that straight up there. So you can do HTML saving and JSON saving, and then you can embed those JSONs to different places. What you can also do is that you can even create this shareable link, with basically just creates a huge link that then you can like send to somebody, and they can open the link with this 2 URL thing. And because like Vega Altair underneath it uses this, like you will get this sort of a link, and if you open that link without the quotes, you will get this. You can view this in this Vega editor. Do remind that a reminder that when you like send this sort of a link, it encodes some of the data needed to plotting the data into the link itself.
It encodes all of the data that it needs to plot
to
this.
do the plot.
So everything that's in the plot is in the link.
Yeah. So basically, like if you like have some, I don't know, private data or whatever, like make certain that like nothing.
Don't use that.
Yeah. But if you want to send something for your friend, like you can just send them a massive link, and that will they can view the plot. Okay, there's other things you can do. So let's look at some fun new. Let's do some fun things with the visual channels. So here we have like daily data now of snowfall in Tromsø and Oslo. and we'll do the usual like kind of like date conversions and limit us to a certain date range, and then we can plot the data. So here we have like now we have the date and there's no depth as X and Y channels, and then we have the column as name. But what if we now colorize this based on another column, like maximum temperature? So what we get is this. So now the color corresponds. So we have like a 3D plot in a sense. Of course, like it's 2D, but the color represents another piece of data. So we see that, okay, there's like some warm days, some cold days, and we can see that if there's a warm day, usually like the like if it's a dark after the dark band in the snow data, usually the snow starts to go down. Like, well, it's hotter. The maximum temperature is higher than, well, the snow melts, and otherwise, like, it might increase. So we can represent this sort of stuff over here. We can also like change the colorings. Like over here, we change the color channel, so we can change the scale. Do you note that like when you're using these colorings and stuff like that, you usually want to like uh, there's the whole subject of like perceptually perceptually like correct colorings, and many of these, like you want to check matplotlib and for Altera and various other libraries, like there are these colorings that are designed for plotting scientific data, that where the idea is that like certain, like human eye recognizes certain like brightness changes or color changes differently. So you might want to use plotting like this to make certain that like the actual like luminosity or intensity of the color represents actual ranges in the data. Like if you have a data that, like, otherwise you might see artifacts. Like for example, in this rainbow coloring, it's pretty like I'm pretty certain the changes aren't that drastic, but it looks very drastic to our eyes. That like hey, like the days are completely different, but like actually they might be very similar in the data values. So when playing with these colorings, don't only look for the coloring that looks pleasing to the eye, but also check that the coloring is like this perceptually neutral. There's also the question of like accessibility of does the coloring have colorblind like taken into account and that sort of stuff. But there's like whole books on this, so I won't go too far into this detour. But when playing around with colorings, it's good to reminder that like sometimes choosing a coloring is more than just the looks. It's also like, does it represent the data correctly? Okay, let's do another plot but this time with circles. So let's try this one. So over here now instead of mark bars, we use mark circles. So we can do stuff like this. Like we can plot things like this. We can like it's not in the material, but in Altair you can also like add multiple layers to the plots. Like you can plot lines over dots and stuff like that, if that makes the coloring easier for you. But let's not go to that because we want to go to the other things as well. Okay, so we have talked about the visual channels a lot, but can you, when you're taking the data into Altair, like there was a good question in the notes that should you like first, like what format should the data be in? Like should you do all of the data transformations before you plot them? And that's usually a good idea. Like if you know what you're going to be plotting, it might be a good idea to like to pre-calculate the data as far as possible and then just plot it. As long as it's in this tidy format, you can like do that sort of things. But sometimes, especially when you're exploring the data, you might not know what is the, like, what are you going to be plotting? Are you going to be plotting like monthly data or weekly data or daily data or whatever? And in Vega Altair, there's this powerful data transformations that you can use. So these data transformations, basically, they take the initial data and then based on the channels, like whatever transformations you do to the channels, it will modify the visual channels so that with those transformations. So for example, in this transformation, in the original data, we had daily values. But let's say we want weekly values. So in here, we can use we can take the original code and instead of using the original code, we
So this is what the original gave, which is just for the few days from December to May. And this is the transformation where you actually look over the whole year because you do it by week. And get a yearly picture.
Yeah.
And I would actually say it's not just if you want to play around, it's also this is some kind of visualization question. This is not a data question. So the pre-processing that I think we answered in the document is mostly concerned if you actually need to modify data in some way or form, not how you visualize this. And this is more how is the data actually being visualized in the end.
Yeah, the only reason why I mentioned that, like, sometimes you might want to do it beforehand is that, like, if you do the data, like, let's say, averaging over a week or something in pandas or in other frameworks such as that, you can get a more, like, visceral feeling of like, okay, this has been calculated correctly. Like with the Altair transformations, of course it's calculated correctly, but with any kind of like system that is like a library or something, you usually want to make certain that the results are correct. So like the plot, it's actually plotting the right data or the right thing you're doing. And I'm not saying it's not doing it over here, but it's like the more complex the system is, it's easier to like not be certain that you actually like calculated the averages correctly. So that's why I was saying that usually like in the exploration time you would do this, and sometimes you would calculate the weekly averages yourself to verify that these are actually the correct numbers. But how these aggregations work, or these transformations, is that in these transformations, if you want to show the code for that generated the plot, so we have data transformations, like there's multiple of these, but in here we use a data transformation for the date, so the x-axis, and we tell it to take weeks. So we want to convert it into weeks. And what it does, basically, at this point, it does a group by, like, it groups the data into weekly bins. And then for those bins, we can do aggregations. So like a mean value, like the mean snow depth, instead of like just plotting everything in that bin. So we calculate the average of that bin, the weekly thing, the weekly mean snow depth. So yeah.
I just want to say in this case there is not the weekly average is because we have the daily values. And it's not an average over multiple different years, which this could also that's kind of the one of the risks with a plot like this. This could also be something that is visualizing the average things over multiple years.
Yeah, sure. Yeah, like
it's a bit from the plot itself, it's unclear what exactly is it.
Yeah, but in this case we have had data from 1 year, so
I'm just saying that this is the kind of thing where you probably with access labeling and things, you should make clear what is actually in the plot there.
Of course, yes. You might use something like year week or something. I think there might be, I don't know if there's such a channel there.
Let's continue.
Yeah, but basically the idea is that you can use these transformations to quickly convert the data into a format where like you can plot it in various kinds of like ranges and things, and automatically do some aggregation. There's also like the possibility of using different like modes, like yeah. So I think it's alter theme nowadays. Yeah, I have to update that one. I think it's alter theme dark.
Yeah, and then we actually get to our final exercise.
Yes. So
What?
so now you can pick and choose what looks good to you in the in the examples for Vegalter, and then yeah, check some of those and try to implement those. There's other things that we don't have time to go through. So for example, I use nowadays Vegalter quite often with I do interactive plots with selections and whatever. Like you can do interactive plots with selections and stuff like that, but that goes way deeper. So if you want to like visualize data and have like clickable elements in the plots for notebooks and stuff like that, you can do that in Vegalter as well because it has this web support. But let's not go there. Let's that's something for that you can look for later, maybe in the examples if you want to look at those examples. But now let's have an exercises until well,
For the last 10
11:35.
minutes.
Let's have 15, so you have time to go through. So 11:35. Let's return then. Bye.
Welcome back.
Hello. So yeah, so now we have gone through plotting. So we have a quick session here about we talk about a bit about like data handling with and working with data with pandas and all of the different frameworks. The reason why we want to mention this is that this is like there were a lot of questions there. For example, like with Vegalta, where do you should do the data transformations and do you do it with pandas or whatever? And usually like the getting the stuff into the right format and getting the stuff right, like for whatever simulation you want to do or code you want to run or something, like the data part is usually where like people, well, everybody has the most trouble or uses the most time. There's been talk that like in the field that like 80% of time with data analysts or whatever they use like for data pre-processing and data handling and data kind of like cleaning up and that sort of stuff. So it's very important subject to be mindful of. It's not the fun part. Like the fun part is the actual like writing the actual model or simulation or like the actual science like that does it. But there's the first, in order to do that, you usually need to have the data in a correct way that you can then do some sort of like analysis from it and at the end like do some plotting from it and then do some papers with it. But in for all of this, the important thing is that at the start you need to have the data in a correct way.
And unfortunately, it's also not something that where you can say, okay, you always do pre-processing like this, because the pre-processing and the data wrangling is very much topic specific. So we can't go into any details here because it would just not be applicable to 90% of the people, each individual bit. And that's why we are in this working with data focused on a larger picture of things.
Yeah, and there's no like this section is small. It doesn't have exercises, so you can just focus on what we're saying and don't no need to like check on the Jupyter that much. But so when we are talking with data, what Thomas just said was like there are million of these formats, and whenever somebody thinks that okay, I have one tool to solve everything, they just create another format. So this XKCD highlights this perfectly. So if there is like a thing that needs to be like represented somehow, like somebody creates a standard around it and suddenly there's yet another standard around it, so that happens. So there's no like one way to represent data, but there's usually like ways that, well, there's better ways and less less good ways, and we'll talk about them later. But usually but there's no one way of doing it. There's so many different ways of doing it. But what is important is to recognize that okay, like there's the question of okay, how is your like what sort of data are you dealing with? Like what is your data structure? Like, and recognizing that is important before you start picking up any sort of data format. So for example, if you're dealing with like tabular data, like the tidy data format is the most common way of representing that, both for the computer, like when you're doing stuff with pandas, but also like when you have a table or something, you want to have it like represented like that. Or when you start plotting, you want to have it represented like that. And even if you're not doing like, let's say you're doing physics simulations or something, and you think that okay, like my data isn't in tabular format, I don't care about this, but let's say you want to calculate something like you want to represent an average of the like temperature of the system state over time or something like or how it scales like or something like that. You have an x and y axis. Well, again, you have something that is like a tabular data or like how many simulations you did, which simulations you did with which parameters or whatever. It's tabular data. So even if your like simulation data isn't like that, the end result is usually represented in a tabular format. And if you're doing like these big simulations, you often use like this kind of like block way of representing data. So you have arrays then. So for example, NumPy arrays are usually like multi-dimensional. They can be one-dimensional, two-dimensional, three-dimensional arrays. And you can have them like stored in a different way. But if your data is this kind of like block data, that's different to this kind of like tabular data. So it's good to recognize what sort of data are you dealing with. And so do you have this sort of like blocky data, like let's say 3D simulations or something, 3D space represented as a big block of numbers? Or do you have like economics data that is like lots of tables? So and for these different tools, like you wouldn't use an Excel to store weather simulation data, and you wouldn't use weather simulation data to store like Excel spreadsheets. So there's like a tool for each one of these purposes. And Thomas, maybe you can explain, what do you look for when you now need to pick a tool? So you need to pick a file format for your data.
So I'm looking at it from a couple of different angles. I'm looking at what is a good way to represent it, and at the same time also what is actually being used currently in the field that I'm working in. Because there is a bit of a trade-off. You could have a perfect tool for something, but if no one uses that perfect tool, whatever you do, it will be extremely incompatible to what anyone else is doing. And you can try to get this now as a new standard, but yeah, maybe it's just not worth it because the tools that are currently being used are fine. And then better don't have another standard. That's this XKCD here. And apart from that, yeah, really looking into what is a good tool to be used, or how can I represent my data in a usable fashion, and also what's my target audience. Is my target to create data that a human can quickly inspect and have a look at to figure things out themselves? Then I would like to have something that's human readable. That could be a CSV, that could be a JSON file. If I want something that is only to be processed by a computer, I would definitely want to go into some kind of binary format because it doesn't need any parsing anymore and it's a lot more precise. For example, with CSVs, if you have floating point data or any non-integer numeric data, you have cutoffs. You have certain precision cutoffs, and that means that if you do a simulation, store it in CSV and load it again, the values have changed. Not a lot, very minimal, but depending on your simulation, that can cause a lot of problems.
Yeah, like the double precision floating point number has like 15 to 16 precision points of like precision. So like if you have a CSV file, either you need to have like huge numbers there, like huge strings of text to represent everything, or you truncate it somewhere, and now you introduce like an error that can propagate throughout your like analysis pipeline. So it would be better to store it in a binary format that stores it as a floating point number. So then you can like keep the precision.
And in most cases, you also, when you store it as text, you're blowing up the size of it. Because the precision in a floating point is as compact as it gets. And if you put that into a string, yeah, even if it's less precise, it takes more data. So you're wasting data, and that becomes a particular problem if your amounts of data start to get large.
Yeah, and when it comes like data comes large, what often happens is that like the question of like do I actually need all of my data with me to answer a question, it becomes important. So when you have to answer like a question based on data, like whatever it is, the question you have to answer, it becomes more important to not load everything into memory. Like the more data you have, like if you just load all of your data into memory, but then decide that actually I just want this one column, like the rest of it just like I don't care about it. Usually what happens is that the rest of the data is still stored in memory. Like you
But
you have allocate it into memory, and suddenly your code requires a lot more resources and a lot more, well, power than um, is
Actually
necessary.
necessary. Yeah.
Yeah.
And even if you would really discard and purge the memory again, you will need this short time where you need all the memory. So yeah, having a format that from the format itself can tell, okay, if you want column 10, I go to this position in the file and just read that. And just read this bit of the file and give you that bit of the file. That will help a lot, or it will make it a lot more sufficient.
And many of the data formats, like the more advanced data formats, they also make it possible to like pick what data you want from the data. Like you don't necessarily have to load everything all at once. Like with a CSV file, you usually have to load the whole file at once. But with many of the advanced formats, you can tell it that, okay, like I just want this column and it will only load that column. But there are so many of these formats that we don't possibly have like capability of going through them. So we have this kind of like not exhaustive list, but quick list of like explaining various kinds of like data formats that you can use. Like if you load raw data from the internet, it's often like CSV or JSON,
JSON,
yeah, or something like that.
especially in web communications. If you have APIs, it's very often that you get some kind of JSON responses that you then need to process. You can also get files, of course, so binary files, but it really depends. And
Yeah, yeah.
and for example, going a bit in this list, so there are advantages, disadvantages to most formats, and it really depends what your specific topic is. For example, if we take let's say pickle, so the Python export functionality, that's great because it essentially can store any data that a Python object has. However, it comes with its own problems, like you need the right versions loaded when you actually load the data, because if the data format, the internal data format of a library has somewhat changed, then suddenly the pickled data file is corrupt because it can't be interpreted anymore because it doesn't know what it is. So pickle is something where, yeah, it can be really powerful because it can store anything, but you need to make sure that this is, but it's not a format to transfer information,
Yeah.
I
It's
would say.
usually also not recommended for sharing information because it has its own, like you can put arbitrary code in pickles, so it's not something you want to like load, like you don't want to execute random code that somebody else has like given to you, so it's not the kind of a format that you would want to use for long term. But if you have like a situation, like often like we think of this like analysis kind of things that we start from the data and we have the original data and then we just like keep it along the way and we just do everything with that until we get to the end. But often in a case like a simulation or like research problem that you're trying to solve, you need to create like an intermediate representation of the data, like something. You take the original data, you clean it up, like do some pre-processing for it, and you may store it into some format that is easy to use for your actual like analysis code, and then the results you store again like in some way that makes it easy to share with other researchers. But there's this kind of like intermediate step where usually you want to pick something, like you can store the state of your system temporarily, like just like, okay, like this is a checkpoint, or this is like the after pre-processing the data looks like this, and stuff like that. And usually you'll want to do this to make your code more efficient, but also like separate the different stages of your code and make like make it certain that, okay, like after your pre-processing, you don't have to do the pre-processing again. It's done. Now you have the intermediate step, and then you can continue on your way.
Yeah. I would bit there's this huge distinction between binary and textual formats. And I think it's good to kind of remember what the things are for. What are the good and bad things with it. And it's pretty clear that on binary file formats, they are on tendency more efficient if they are being used by a computer, if they are being used by a program, because they can store data more compact, they can more easily access individual pieces of the data within the file and so on. But of course, the disadvantage is they are more specific. So you need to have something that can parse them, because a human looking at this, sees ones and zeros, or hex code, or however the editor that they are looking at it. And then, it's more prone to not be compatible. Textual formats have exactly the kind of the opposite of that. You can read them quite easily because they are just text, but they are prone to imprecisions, as mentioned before. They can be, or they can and very often are relatively slow to read write, because you can't just hop into a certain position. And you need to read essentially all data to get to a certain point. And it's almost impossible in textual data, or not impossible, but quite difficult to get really multidimensional data in a textual format. You can get it leads to a very, very strange replication of a lot of elements. You can do something like that in JSON, but it's blowing up the amount of data that you need to store, because you essentially need to, for every dimension, you need to replicate the identifiers every time. Because you can just think about it. You can't really put multi-dimensional data on a piece of paper. You can write it down, but then you replicate things, or you need to know additional information.
And at some point, like the data becomes like basically like once you have enough like JSON files or whatever, you anyways need to use computers to read them. Like you won't go through it by hand yourself. Like say CSV, you can read it if you look at it, but like for many like complex data formats, or like once you get enough complex enough data, you eventually will use computers to read them anyway. So it becomes important to like understand what's in your data and what's the format there. There's also like the whole question of like we also already mentioned that it's important to pick a data type in your field. So like as a general like consideration, or kind of like things that you like good things to check, is that is somebody else like else using this. So for example, like previously there was this GeoJSON mentioned. So if you're doing like map data, if you're trying to do like if you're dealing with map data or something like that, there's like GeoPandas, there's this whole ecosystem of like how do you deal with different coordinate systems and mapping data and stuff like that. If you're doing physics simulation, there's different formats for that. And like usually you want to pick out what is important for your field. Like what I usually do is whenever there's a new tool that needs to be used, I look at what are the import and export functions of that and check, okay, what does this need? What does this tool use? What representation it wants from me to be able to use this tool? And then try to wrangle my data into a format that the tool uses, so that it can utilize that. And it becomes very important also for like replicability of your like how can you reproduce your results? Like if nobody else can reproduce your data, or like wrangle your data into the same format, it's very hard for people to replicate your results. or reuse your code. Like if you have a code that does an analysis, but the input needs to be in a format that is like you need to have it specifically tailor made for this kind of like weird format, then suddenly like nobody will want to use that. So if you want others to be able to use your tools and what you have created, you really want to pick something that, well, others can use and others can utilize.
And
So
even if that is maybe not the most efficient for your particular case, because yeah, it's a trade-off. It's something that might be the lowest common denominator for all the different types of analysis that are done in this field is this format. Yeah, it has its disadvantages, but we can do everything with it. So yeah, each subfield in the field might have a perfect thing for them, but yeah, then it's not transferable, or it's
and
extremely difficult to transfer.
and when we started today already like talking about okay like how these different tools play together, like NumPy is the building block at the start, then pandas is the representation of like okay how do I represent multiple of these arrays into like a cohesive data set. And
How do I
we
get the different formats again together?
yeah
Because
yeah like
X array, one X, sorry, NumPy
yeah
this is one data type, and yeah, but we often need these multiple data types in one set of data,
yeah
and that is something that NumPy can't do.
yeah, and we often want to transfer that information to the next piece in our tool set.
Yeah.
So when we have NumPy arrays, we put those into pandas. When we have pandas, we put that into Vega Altair to get plots out of it. So we often have this kind of like a situation where like some framework or something decides that, okay, like this is a good decision. And it's not like the like decision by fiat or like just because we say it's that. Like I often think of it is that like all of the decisions made to create these frameworks are paved with problems that have been solved. like there's this saying that like workplace regulations are written by blood, so that like every if there's an accident, like some regulation comes out of it, and there is some reason why this regulation has been created. And with kind of like frameworks, it happens the same kind of way. Like people have tried to figure out solutions to answer their questions, and eventually you only see the endpoint. You see the regulation, you see the framework that okay, like why does this require me to give it in this sort of format? The reason is somewhere there, but it can be like 10 years ago, like somebody realized that this is a better solution for the problem. And I personally appreciate it a lot, so that we can like build upon the shoulders of giants. Like we can build upon like the work done by previous people. And that's why I often like to use these tools. And this is also important because like if you want to go further, like if you want to, like we are now going, like we are looking from NumPy to pandas, but there's stuff further away there as well. Like there's like the big data analysis pipelines. And we don't have time in this course to go through like Polars and IBIS and other like this kind of like tools that can like leverage, like if you have a big data warehouse or something in a company, or if you have a lot of big databases that you need to analyze. In those cases, it's mandatory to use their way of doing stuff, because otherwise you can't like really access even that data. Like you can't just like ask, like if you're working in like I don't know Google and ask for like a huge number of data, your computer would explode. Like you would want to be very precise on what sort of data you want to request from these big data warehouses. And in those cases, it becomes even more crucial to like pick the way that is designed to like solve these questions. And it like limits what you can do, but at the same time it gives you more power. And so it's not like really a trade, like it's not a trade-off of like liberty for it's like some you give up some liberty to get more done. But I think with that we are reaching the end of this session.
Yeah,
Thank you so much, Simo and Thomas. It is now time for a lunch break. Some people in the comments yesterday were suggesting to skip the lunch break. I believe we need to eat and it's important to eat. So we will be back in 1 hour. You can still use the notes document if you have any other questions. And I will not steal any more time from your lunch. So see you in 1 hour. Bye.
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 Hello, hello, and welcome back from the lunch. So you've been active with the notes. There are very interesting discussion, especially when working with the large data sets. We try to answer it a bit, but feel free to, ask more and discuss more. But now for something completely different, or is it completely different? I don't know. Well, first of all, I want to introduce a new instructor with us today. It's Luca. Luca, do you want to say something about yourself?
Sure. So, hello everyone. I'm Luca Ferranti. I'm RSC at Alto, and I will be talking about this lesson about scripting in a few seconds.
Yes. And in my opinion, this is just my personal opinion, this is the most beautiful and most important lesson out of the whole course, because you will really realize that Jupyter is just a way to prototype and familiarize with Python and with data science. But when you need to scale up, when you need to consider reproducibility using remote systems like high performance computing clusters, this next hour is, you will go back to the materials from this next hour on how to write Python scripts. So I will not steal any more time from our instructors, and I let you go with the Python scripting.
Introduction for the pressure of delivering the most beautiful lesson according to you. So, hello everyone. Now we're talking about scripting. So, why do we want to create scripts? Why are we not happy with Jupyter Notebooks so far? Well, Jupyter Notebooks are great for exploring, for prototyping, which is what we do a lot when we do science. We do research, we generally don't know what we are doing, we want to try, we want to get instant feedback. Maybe we want to blend our math notes with our code, with pictures to get a gist of what we are doing, of our research, our work. Then now we are slowly moving towards the next step, where we know what we are doing and we have found actually something that works. So we have developed a nice tool for doing some analysis. We have tried with some parameters, with some values, with some data, but now we want to generalize it, to make more generic. We want to make sure that everyone can use it with different data, with different settings, and so on and so on. And we wanted to make this process of tweaking different settings, tweaking different values as easy as possible. And the limitation with Jupyter Notebook is that it's this blended text of code, pictures, text, with a lot where if we want to change values, we should edit the notebook directly. So open it, go through the code, find the right place, change the value, and so on. And this is not very ergonomic. So we want to find a more dynamic way of doing this. And I'm not alone here. I have my great co-teacher, Thomas, who will also deliver questions from the interactive notes system. So whenever you have questions, you can interrupt me, ask questions, and we will address it together. So, Thomas, do you want to add something so far to this introduction? You want to?
Not a lot. The only thing, to me, moving away from notebooks to scripts essentially allows you to build the actual final script in some way that then lets you go through all of your processing steps and allows you to also separate your code into different parts. It's something that we are not covering here, but for example, in the Code Refinery Tools workshop, there's a lecture about code modularity, and that allows you to reuse things a lot more easily. Smaller things. At the moment, we are mainly looking into reproducing the large run and avoiding the problems that sometimes come with Jupyter, as in you are not entirely sure about the execution order and things.
Yeah, exactly. So, cool. So first of all, maybe I should clarify, what does it mean to convert to a script? Maybe it's not obvious to everyone. What does it mean in the first place for something to be a script? Well, for now, we can think of a script as a simple plain text file, so like Python file, which we can run from the terminal. Yeah. And the first step now, if we're using Jupyter, it's actually pretty cool because we can very easily convert our Jupyter notebook to a script. The Jupyter Lab, Jupyter offers us a very compact command line command to convert the Jupyter notebook to a plain Python text, which we will call script, where then we can add all the bells and like cool features for more interactive usage. And if you have Jupyter installed, this is the command that you can use running from the terminal. So Jupyter nbconvert --2 and script and the name of your Jupyter notebook that you want to convert to script. And let's try to break it down a bit, like why it's written like this, what does each part mean? So Jupyter, well, Jupyter is what we're using so far, what we have been using to write the notebook. nbconvert, so convert a notebook to a script. And then we tell it what is the notebook that we want to convert. And what this will do, it will basically take the file, convert all the text or like the markdown cells into comments if memory serves, and put the strip the code cells from being cell and just put them as plain text. And this is then something that can be opened in a plain editor. So without further ado, yeah.
If you could quickly, so how to run that command in the terminal. There's also a simpler way to just run from within Jupyter Lab. So if you could switch
totally.
to the Jupyter Lab tab that you have.
Totally.
You can.
So I'm going to give a bit of like, let's say, spoiler for the next exercise, that if you have a Jupyter Lab open, what you want to do, you want to click New and Terminal, and this will open the terminal for you from which you can run the command. And maybe one important thing to clarify is that you probably want to make sure that you are already in the right folder. So when we will get to the exercise, you will see like how to download the notebook, and I recommend to start the terminal from the same folder where your notebook is. And then you are able to run the command from here.
And don't worry, your shell or your terminal will probably look slightly different to what Luca has here because it's essentially using the terminal of your operating system, so whatever you have configured there.
Yeah, I have slightly customized appearance, so yeah.
Okay.
Cool.
And I think with that we.
So I think actually in this session we start with the first exercise, which is setting up the conversion to script, and then we can start looking at the notebook together and see how we make it a nice script. So I would say we can go to the first exercise, which you can find in the teaching material, which requires you to download the notebook, open it in Jupyter Lab, launch the terminal as we just saw, and convert it to script. And then you can try running it also from the same terminal with Python or Python 3 and the name of this new script.
Okay, and I think we are giving a good 5 minutes for this because it's relatively small and should hopefully run without any problems. But if you have problems, just write them in the collaborative document and see you back in 5 minutes.
Yeah.
Bye.
Hello, welcome back everyone. Now we are going through the solution of the first exercise, and we will create the first version of our script from the Jupyter notebook. So first, let's open the notebook and have a look at it. So I hope you managed to download this weather observations notebook. And let's have a quick look at it. As you can see, it has like a simple, like a typical structure of a typical, I would say, like, data analysis or analysis researchy application. So we are downloading some data, we are doing some filtering, extracting some data, and doing some plotting. So would be kind of, the first step of your analysis, where you just, have a look at the data, what data you have, what do they look like, and you prepare to think what to do next. And this is now as a notebook. And as we were hinting before, a notebook can have some limitations if you want to reuse the code in slightly different setups. So now we have hard-coded what data we use, what dates we use for the plotting, and this is a very rigid structure. And we wanted to make it a bit more flexible, a bit more reusable in different setups. And converting a notebook to script is the magic word to make something, or well, the first magic step to make something more reproducible and more dynamic, more scalable. And yeah, I mentioned that now this is very rigid, so maybe if you want to use in different setups, it might be a bit painful. What do you think, Thomas? What if I gave you this notebook? I told you, hey, I have this very cool data analysis pipeline for weather data. Here is my notebook, and you want to try with different setups. What would be your pain points? What would you find painful in this notebook?
One thing that I would find a bit painful is that we always have to essentially do the whole pre-processing again and again, or at least run the whole cell again and again each time. So that this start, even if we just want to change the start dates that are being used, if you just want to have a different time range, I will assume that yeah, taking a different source for the data is okay. That's okay for me, at least at the moment, because this is something for these weather observations that come from this data plot. So yeah, fine. But yeah, having to rerun the whole thing when I just want to change the dates is something that's a bit annoying.
One thing, if I look at this, one thing I would find painful or dangerous is that now, I need to read carefully through everything to find where is where. And a mistake that I can very easily imagine myself making is that, I want to change the dates. I find, okay, let me see, here is start date, here is end date, I change it.
Yep.
But oops, here is the name of the picture, and I forget to change that. And so when I rerun it again, I change the dates, but actually it overwrites the previous picture. And now my picture is not with the old dates, it's with the new dates. And this sounds very scary if I'm preparing pictures for paper.
I can actually imagine something more that is problematic. So you change the dates and you change the output, and then you run the second cell again, but you haven't actually run the first cell again. So you still have the old data. And that's where this becomes really dangerous, because then you have a new file for with a new name for the supposedly new data, but it's the old data. So it's just the wrong data that you're presenting there. And that's also to me why I'm not a huge fan of Jupyter notebooks for final scientific work. For prototyping, fine. For testing things out, perfectly fine. But if I want to run my analysis in the end, they are too prone to these kind of I forgot to execute one cell situations. Or I ran the cell again and it actually changed data in a way that I didn't expect.
Yeah, talking on behalf of a friend, it's a very common mistake to forget to run some cells. So I think we have bashed Jupyter enough. Maybe let's start make it better. So as I was mentioning, we can open the terminal from Jupyter Lab, but now we'll do it again so that people who didn't see before are able to follow. So now we want to start converting this notebook into a script. And like one way we could do it is that we manually create a new file and copy paste the text, but that's a bit like, maybe clumsy. So what we will do, we will open a new terminal. So if you're in Jupyter Lab, from File, New, Terminal. And now it will look a bit different for you. This is like my custom terminal. But now we want to make sure that we have, that we are in the right folder so that we have our notebook. And then we can run the command. So Jupyter nb convert --to script and the name of the file, weather observations.epub. Let's do it. Whoa. Something happened. Let's see. And now we have a new file. So now we have converted the notebook to script. We can open the file and have a look at it. So you see from Jupyter Lab, now I have this new file, which is weather observations.py. So it's like a plain Python text file. Let's open it. And now we can see what happened. And now we can see what our command actually did. It actually did what we could have done manually, nothing much more. It took the text and copy pasted into a new Python file. And one thing to highlight is that what was before text, like markdown cell, now it has become a comment in the script. So what do you think, Thomas? Is this a good script? Are you happy?
Well, I'm happier than before because now I don't forget to run certain cells, but I would still need to modify the script every time I want to change things like the start date or the end date. So having something where, because if you can run this script by just saying Python and script, and
maybe we can try it. So
yeah.
So now, so it could be Python or Python 3, in my case, Python 3. And then we want to run the weather script. So now it's important we choose the .py, the script one. So with Python, we run the script.
And this
it's a warning.
And this generates the output image. At least it should.
Yeah, at least it should. We can check later. Okay. Yeah. But yeah, we could run it. But what do you think? It's a bit annoying now.
Well, as I said, I would personally like to be able to switch to different time ranges or change the output file name so that I'm not always writing the same output file name. That's
so so for example, you would be able to do something like Python 3 weather observations.py and then pass the dates from here, for example, so that we wouldn't have to open the file. So I guess we can start doing it. And the cool thing is that Python makes it very easy for us to do. It allows to have this, we have this sys library, like built in Python to pass simply some simple arguments.
General system information.
To get system information.
And part of the system information is the arguments that your script got, which is a bit unintuitive from a Python perspective, because the first argument that your script got is actually the script itself, because it's not the arguments are not the arguments for the script. The arguments are the arguments for Python, and Python gets as the first argument the script file.
So maybe we can take a short demo for it to demo. So what
so you
we want to do?
Import sys.
Import sys. And now, for example, here, instead of having the hard-coded date, we would use this syntax of sys.argv1. And this is what you were referring to, that in Python it's like starts from 0
and the 1 and not the 0 here, which coming from a Python where it's zero-based is a bit unintuitive.
Yeah.
And, you
And
can
then
do
we
this,
want to maybe also
do a
parameterize the end date.
Mhm. Yeah.
And should we parameterize also the name of the image?
Well,
Oh.
it definitely makes sense to do that because
Yeah.
that
I also realized I was on the wrong file.
you were in the
Yeah. And here we can add the, so maybe we can make a variable output file name, and this would be sys.argv3. And here we would save the picture as output file name.
Okay,
yeah.
Let's see.
Should we try it?
Yes.
So for so what we did now is that we used load this library sys, and what this library allows us is that after we write Python 3 weather observations.py, like we did before, now we can pass some inputs to the script. And here when we say 1, this is like the first argument after the file name, so the first thing we pass. The second argument after the file name, so the second additional thing we pass. And this is the third thing, so the third thing after the file name that we pass. So this sys.argv and the number is like the nth thing we pass after the file name that we can pass from the terminal.
It's the system argument
now
vector.
we can, yeah, 0, 1, 0, 3, 2021, 3105 2021, and spring in tapiola.png. Let's run it. And now we have a spring in tapiola.png image appeared.
And
Here
this
it is.
If you compare this with the weather.png that we had before, this is different. Because we have a set up a different time range for it.
Yeah. Are you happy with this solution? Because I have a few gripes.
Well, at least what I can do now is I can essentially select different points from the data. So overall, yeah, it's okay. It feels a bit like, okay, I need to remember the order of the arguments when calling it. I need to make sure that, okay, is it actually the right order? And so it would be nice if I could give it a bit more specific things so that I can see from the command call what's the start date, what's the end date, what's the file name. Because like this is prone to someone thinking, okay, the first is the end, the second is the start, or something similar. And that's why I would personally not be that happy about it. But it's definitely a lot more reusable than it was before, because I don't have to touch the code without while changing what I want to plot.
Yeah. I also have a couple of other issues with the current setup, which is much better. So first of all, you remember first I complained that if I want to change from the notebook, I need to read everything and find where to change. Now I still have to read everything. I still need to read the whole script to know like what to pass. So like if I just send you the script, if you just send me this script, I maybe say, okay, it's a script. But now suppose I don't know that I need to pass these parameters as input, and I say, okay, it's a script. Let me just run it as we did the first time. Weather observations.py. Now it gives error list out of range. And I'm not super happy with having to open the file, figure out, it's a bit annoying.
Yeah.
And also, what if I only want to change, for example, the picture name, but I don't want to change the dates? I don't want to type again the dates. I want to use some maybe default values, or if I have a lot, I I don't want to remember in what order to pass. Like, is it a picture name, start date and date? Is it start date and date, picture name? I guess I can assume it's for start and end, but so yeah. So what we want to do now to generalize this workflow to increase our ergonomicity, I would say ergonomicity of scripting, is that we have seen this library SUS, which is pretty simple, pretty bare bone, but it's also a bit limited in what it can do. So what we want to do now, we want to upgrade, level up our scripting workflow to use a library called argparse. There's a few other options, but I would say we use here argparse because it's built in Python, it's nice, simple to use, gives enough functionalities, then in life one can ever go fancier and fancier. Yeah. So just to take a quick anchor point of where we are now from the notes, we discussed the use of this SUS library, which is this very simple bare bone library to accept inputs from the terminal. Now we are moving to the second session here, to the second part, where we want to discuss the usage of this library argparse.
How exactly
How
exactly does argparse run these arguments, or how do you define what's coming in there? Is that an argument I see down there, right?
Yeah, so there's a short example that we can use to like this. So we have a shorter script that we can use as an example to like get to know argparse before using in our weather observations. Do you think we should type this or just go through it?
I think you can
textually?
just copy paste it over and
yeah. And if you do copy paste, one thing I would like to highlight is that there's a short typo here where it says type equals string. This should be str. I have actually opened PR to them and ask you a review of that, but yeah. But yeah, so now we want to get to know this argparse library, and before we use it in production, so to speak, with our weather library, we will take this toy example to get to know our new friend. So now what I will do here is that I will copy this text from the notes, go back to Jupyter Lab, create a new Python file, so file, new, Python file, and paste this text. And now, as I was mentioning at line 7, where it says type equals string, I want to fix the typo so that it should be type equal str. Let this be a proof that I actually checked the material before starting teaching. Yeah. Okay, so let's comment a bit the structure of our file. Here we are loading the library, so import argparse. And here we are creating this parser object with this argparse.argument parser. So we are creating a class here, but it's not important. And now what we want to do, this parser is like this enhanced SUS to read the inputs from the command line. And now we want to tell this like super SUS, this enhanced SUS, what are the arguments that we are accepting. And here we have two ways of doing it. Defining a positional argument or define an optional named argument. So when we define positional arguments, we are doing something very similar to what SUS was doing. So we define first, second, third, and they need to be passed in order. 1, 2, 3 positional arguments. Now, so here we add this argument, which we call name. We are telling it it's a string, so str stands from string, as the previous typo was hinting. And this meta var, well, we will see in a second what it means. It's kind of like, imagine it's a variable name. Yeah, I mean, it's a variable name. It's like giving a name, like as if it were a variable. And then something very nice that connects to what we were saying before is that now we can actually help people without having to read the whole script. Like before I was complaining, I still have to open the script, go through everything. I still need to open the script, read through everything to find out what I need to pass. With argparse, we can make some automatic documentation so that lazy people like me can get some help and instructions how to use it without reading everything. So this was the first one. Then optional arguments are useful for 2 reasons. They make it position independent, so I don't need to remember the order. And the issue with like positional arguments that even if I give default value, if I want to only change the third, sorry, if I only want to change the third and use first and second, the same default ones, I still need to repeat them. Whereas here, I kind of fix this problem. And now the syntax is slightly different. This dash d or dash dash date will become maybe a bit more obvious in a second when we run the script, but basically means that this argument comes after the short flag dash d or the more verbose flag dash dash date. So when we will run it in the terminal, these will have to be prefixed by dash dash date or dash d.
And the nice thing is
then,
they can essentially appear anywhere in the command call. So the positional arguments, they can come before positional arguments, after the positional arguments, as long as they are specified with the flags.
Yeah, so it makes like more robust for people with short memory like me. Like where was it? Like where do I put it? I can put anywhere. Yeah. And then the last, let's say like bureaucratic line. Yeah, args equal parser dot parse args. This makes the magic happen. So far we have only specified, we have created our parser, we have told it what to accept. And here we are actually making the action happen. So we're saying, okay, now when I run the script, actually parse the arguments. So, do something actually.
This
and then
This is where argparse essentially calls sys and gets the arguments and then processes what we have told it to do with the arguments.
Yeah. And then the nice thing is that now that I have this argument parsed, before, remember, we had this sys.argv 1, 2, 3. They're not very informative. Now I can access those by name. So I said that this parameter is called name. I can use it doing args.name. I've said that this parameter is called date. So I can access this with args.date. So it makes also the text a bit more readable, because then if I see sys.args v1, I'm like, what is that? Like, how do I know what that means? So without further ado, I will save this file and call it birthday.py. And now we can run it. Now, a cool thing about this argparse is that it also gives me this nice Easter egg that if I now do Python 3 birthday.py --help, it actually prints me some documentation for the script, which was automatically generated from from the specifications when we listed all the arguments. And that's why it's important to use the help keyword to print these nice instructions. So, okay, now I say, okay, positional argument, the name, optional argument, the date. So it's optional, I don't have to do it, so let's go with the minimum first. Python 3 birthday.py. So one positional argument, it needs, I need to pass it after the script. Name, I guess I'll tell it my name. Now, it says Luca was born on 1st January 2000. That's not quite true. So I will now modify the date. So Python 3 birthday.py Luca. And now I want to highlight that this difference between optional and positional argument is that now if I only do a date, I'll use a random one, it actually fails because now the date is not a positional argument. And being an optional argument, it needs to be prefixed by the appropriate flag. So for example, and the appropriate flag is seen from the documentation, -d. So let's go back, which we can do by arrow up. And now before here, -d space. So I said prefixed, but prefix means also with space. And now the date is different. Luca was born on 1st of January, 1999, which is still not true, but it's okay.
Yeah, and you
Nice.
could now
So-
also put the Luca in the end instead of, so move Luca to the end because it will still work, being that Luca is the positional argument and the -d
Yes.
is an optional argument. You could say minus date instead of -d and it would work. And yeah, it's overall a lot more robust and flexible.
Yeah.
Okay. So after
Excellent.
having seen that, I think we can go to the next exercise, which is which has you actually do this change to the weather observations script, where we would like
Yes.
to have the start date and the end date being changeable, along with the name of the input file and the name of the output file. Because then we can actually test different things.
Yes. So what we want to do, we want to go to our script, which I think I lost, this weather.py. And now we have this cryptic sys.argv1, sys.argv2. We want to replace those, the name of the picture and the input file. And we want to do this in a nice user-friendly way using argparse that we just demoed. So this is the exercise in the nutshell.
And
Make Thomas and me happy with this script. I would say maybe we can give 10 minutes. That leaves us enough time to go through the solution after that, or should we just do live?
I would say till 55, and the solution is also and we'll just discuss the solution and what we can do then with it.
Yeah, cool.
Okay, see you back at 55, and goodbye.
Bye. Welcome back, everyone. Now we will go through the solution of the exercise. And if you didn't manage to do everything, that's fine. The solution can also be found from the teaching material, so everything will be available afterwards. No worries about that. So what we want to do, we want to upgrade our script from using SUS to use argparse for better usability. So I will replace the use SUS with the import SUS with import argparse. And now, as we saw, the first thing we want to do is create the parser. We initialize the parser. So parser equal argparse.argument parser. And then we want to pass all the arguments to it. We want to define all the arguments that we want to accept from the command line. And now, in the interest of time, I'll just copy paste this and briefly comment on those. So as we discussed, we want to parameterize input, so the link here, output, so the name of the picture we generate, and the start date and end date. Now, input and output, we are making them positional arguments, which we are calling input and output. They are string, so text literals, and we are adding a short description. Then we are defining two optional arguments, which are the start date, called start, and end date, called end. We can see they're positional because of this dash syntax when defined. And also by the presence of the default value, if not, they're optional, not positional. The presence of the default value, if not specified. Then, as we saw, we want to make the action happen. So what we want to do, args equal parser.parse args. And this will make sure that we actually parse those arguments when we call the script. And now what we can start doing, we can now replace hard-coded constants with the parametrics call. So now we don't need this URL anymore, because this will be the input. So here, when we build the weather variable, this will be args.input. And this we can delete. Similar here for start date and end date. Before we were using SUS. Now we use our upgraded version, argparser. They're called start and end. So I will replace this with args.start and this with args.end. Yeah. And then finally, the last update we want to do is that we want to have the picture name also being a parameter. So I will delete this line here. And now the name of the picture will be our args.output. So I think we are now ready to test our script. So we can go from the terminal to the terminal. Now Python 3 weather observations.py. And now first thing we can do is that we can ask for help since we use the argparser. And now we get this nice description that we have two positional arguments, the input, which is the input data file, the output, and two optional arguments, the start date, the end date, which can be passed with the flag -s and -e, respectively. Yeah. And now we can briefly test. So if we go back to the material, in the discussion session, we have a few usage examples, and we can try running a few of those. So maybe we can, so these we ran already. We can try the second one. So I'll copy this and go back to the terminal and paste it. And now we see we're only passing the two positional arguments, the input and the output. And when we run it, oh, pardon, I need to use Python 3. When we run it, we get the picture. this temperature tabula. We can verify we have now a new picture called the temperature tabula, which we can open. And now, since we didn't sorry, yeah.
I would add one more thing. So by changing all of this, we also have now the opportunity to just download the file and not always download it again, and just provide the file itself, because if there's no URL, pandas will look in the local folder. So that's something that came on top without us actually having any additional work to do. It just made the whole thing a lot more flexible.
Yeah. Yeah, that's a very good point. If we had the CSV file downloaded, then we could point to that directly and would be there usable.
Yeah.
Yeah.
Okay. So there is another part about larger option lists that we will not be covering today. It's mostly concerning if you have a lot of different arguments for your program, then it starts to make sense to really write configuration files that are being loaded at the beginning of the program, and that you don't provide as arguments, because even with labeled arguments, it just becomes messy at some point. If you have a even this web URL call is already somewhat messy again. So at some point, you just want to put all of these into a configuration file, and then just provide the configuration file from which the arguments are then loaded. So you have a couple of different configuration files.
Yes.
And with that being said, I think we are going to go to a break again. And after that, we have Susa and Simo talking about profiling, I think. Okay, then.
Yes.
See you in about 10 minutes at 10 past. Goodbye.
Hello, welcome back. So from the break. So now we are going to be talking about profiling, and we have Susa here as well.
Hello.
Yeah, so first off, like profiling, why do we do profiling? Well, usually we want stuff to be done. So we want to get stuff done fast. So we want to optimize our stuff. So in this mandatory XKCD, you can see like a good example of how long does it take to like how long should you spend optimizing a task before you spend more time optimizing the task, like optimizing the task than actually like saving by doing the optimization. So Susa, when should we optimize?
Well, I generally think it's a good idea to try to optimize if you do something regularly. Like if you do it once a day, and you can improve it a bit, that's potentially likely fairly good savings. If you do something once a year, actually I wouldn't even consider it worth optimizing. If there's a task that is, you're going to do it 2 times, yeah, just do it.
Yeah, often like, yeah.
If you do it 100 times, even if it's just, it will just take you a day to do these 100 times. If you can spend an hour on making it be half a day, there'll be some time savings there.
Yeah, like I think everybody has an experience of that they need to do something and they need to get it done, and then they're like, okay, I don't have time to spend on trying to figure out what's the best way of doing it. I will just do it manually, copy pasting stuff from one place to another, or doing some sort of like running the same script over and over again until your like keyboard is melting because you can press enter so many times. But that's one way of doing it, and not everything needs to be optimized. But often, like when you have some problem and you want it to get done, and you realize that, okay, like this is not happening as fast as I was hoping, so I feel like there's something to be gained here, like there's something that can be optimized. So then the question comes to, okay, what should I do? And the key steps for optimization is like 3 points here. Is first measure. So if we have an analogy of like if you go to a doctor, like the doctors will do tests on you. They will like determine what is the sickness. Are you even sick? Like they will do tests, the blood tests, X-rays, and whatever to determine are you sick. And that's basically what we are going to be talking about today, the profiling part. Then after that, once you figure out, okay, like this is sick, this piece is something is wrong here. The question is like, okay, can you diagnose it? Can you figure out what is wrong? Like, and that's actually a harder question often than like a hard question to often start to like figure out, because often the first instinct is like, okay, I will just throw stuff at the wall and see what sticks. Like I see that this is slow, I will just start modifications, whatever, maybe that it will be faster somehow. But usually it's a better idea to actually like figure out, okay, why is this part slow? Why is this? What causes it to be slow? Like, is it some coding thing? Like, well, of course, it's most likely a coding thing, but or is it just like it's slow because it's doing a lot of stuff? Like sometimes things can be slow because if it's a heavy calculation or something. So this is like creating a treatment plan for your sickness, like doctor giving you like a treatment plan. And the last step, once you know what you're going to be treating, is to actually treat it. So to actually give them medications or surgery that actually helps you with the sickness. So for metalheads, I would also call this like searching, seek, and destroy. So you like figure out what is the problem, figure out where the problem is, what is the problem, and then destroy it. But so how do you figure this out? So the first step course, like is to add something into your code that tells you what the code is doing. So timers are like the simplest approach. So you add some timing like things into your code and you print out what is the timing. Maybe like a better way for long-term health of your program is to use logging. Like Python logging module, you can set it so that it prints timestamps whenever it's doing something. And if you add these to the like major like breakpoints of your code, like okay, now I'm going to a next iteration, now I'm starting data loading, now I'm doing whatever, then you know that okay, like you can calculate from the timestamps that like this period took awfully long. Like I don't know what happened here, but something is off. But this is kind of like a very not very descriptive approach to like figuring out what is the problem. Like you're just measuring like very like okay, do I feel like I have a hot head? Like do I have a fever? Like this kind of like it's not very accurate. So for better way is to use dedicated profiling tools. So these here's a list of some of these profiling tools. Like it's by no means exhaustive again, but it has some like some shown here. Some of these are already included in Python, like C profile and profile, and memory and sorry, trace malloc. They are part of Python itself. But then there's others that are like provided by various places, and some of these profilers are so-called like tracing profilers. So basically, tracing profilers they check each line when you execute. They will check what's being done, what changed between each line, and this gives you very accurate like results of what's being done. But it creates like a slowdown to the code because now it has to like measure everything. So you don't get like realistic runtimes if you're using trace profiling, but you will get a lot more like accurate results. But then there's also like sampling profilers. We'll be looking at Scalene today on sampling profiler side. That basically like every now and then they ask the program, hey, what are you doing? Like, what are you doing? What are you doing? And then they create like a picture out of that. So they don't have such an overhead as the tracing profiler, but they can of course miss something if something happens between the sampling periods. But often like there's some like you can use the sampling profilers to profile like most of the stuff, but it really depends.
Do you know of the ones we listed, which ones are sampling and which ones are tracing? I mean, you said Scalene is a sampling profiler.
Yeah, C
But
profile and
the others,
profile are tracing profilers. I think line profile is as well. I think Pi instrument is maybe sampling, I think. And Pumpler is Pumpler. I don't know how to pronounce this. It definitely is probably a sampler because it uses the wordplay over there.
yeah,
But
and then tracer malloc is probably a tracer.
yeah. So it like does the tracing. So usually you want to check on these, and usually the whole field is called like instrumentation. Like you basically like you put these instruments into play, and then you like measure like small nitty-gritty details of your program runtime. And but the best way of probably like demonstrating is to actually have a demo. So we are going to have a demo now here of a example case. So this example case is this kind of like a traditional Monte Carlo method example of like throwing darts at a dart board and calculating pi from that. So how it works is that basically like the area ratio of the areas, so between the dartboard and the square, is like you can calculate the probability of hitting the dartboard, and like the probability distribution of that is the same as like, well, I'm really bad at explaining this right now, but yeah, basically like the area of the dartboard is pi, and and the area of the square is 4 because it's like 2 to either direction, like 2 squared. So basically, if you throw dice, like random darts to the dartboard and see where they land, you can calculate how many, like what is the pi based on the ratio of hits to throws. So that will like go towards pi. And this is like a commonly used example. So here we have like a small piece of code that runs this. So let's switch into like a Jupyter environment and let's see what it does. So basically, yeah.
Remember to time it, because we do
Yes.
want to measure with.
Yes.
Or
So
do we
over
have
here,
the profiler already in place?
I will set it up. Yeah. So what we have in the code is that basically we calculate the number of hits. So we throw like n darts, and then for each dart we see where it lands. We take 2 random numbers, like I coordinate and j coordinate, might be x and y. I don't know why I called them I and j actually. And then we calculate the distance from the center, and if it's in the square, in the circle, in the dartboard, the radius is less than 1. So then we calculate it's a hit, otherwise it's not a hit, and then the pi is the result. So if we like quickly demonstrate what it does, let's throw like 1,000,000 darts. So we get a bad estimate of pi, but an estimate nonetheless. It's getting closer. So let's now time it. So let's add here time it, and let's add let's say one like let's calculate for 10 million throws, so it will take a bit longer. So this is of course already like a good way of like getting some baseline numbers. Like before doing any optimization, you usually want to determine what is the like baseline speed. Like, is there something to be gained? And of course, this is a toy example, but it would apply for many situations. So in this case, we get that okay, it's about 2 seconds to run this. So let's try to profile it and see where the problem really lies. And for that, we can like take the original code. I will actually, well, I will organize the bit. I will throw the imports into a separate cell, and let's have the original code over here. Because for the profiling, it needs to know what code to profile. It's good to have the same code in the same cell, so that it doesn't go across many cell boundaries, and it will give us the correct answer. So over here, let's do like now profiling. And what I have added here is this magic. You can do this from the command line as well. The C profile has a command line, and it has also like a Python. Like you can do it in Python as well. This instrumentation. But we basically say here that like profile run this, sort it by the total number of time used by some part of the code, and then limit it to top 5. And let's run it. So now the profiler will run the code, and it will give us an output. And this output, like let's look at what we have here. So we have 30 million function calls, give or take, like some over that. And it took like 7 seconds to run it. So we can see that it's slower with the profiling, because this is a trace profiler. It's slower to run. And over here we can see that okay, like we can see the number of calls is 20 million calls to the random method random, and 10 million calls to built-in method math square root. And we can see that the total time, most of the total time is used by these ones. So it's used by these. This is an artifact. The sleep method is an artifact of the Jupyter environment, so we can ignore that. But we can already see what can be the problem. So basically, in the for loop, we currently have like, we do lots of function calls to these functions, and those take time. So okay, let's try making them faster. Like maybe we could make this faster by using NumPy to do it. So let's do like a naive approach of like, let's make this faster, and let's use NumPy to make it faster. So let's use NumPy random and NumPy square root to do the thing. Let's do this sort of a. Did we lose the stream?
Looks a bit like it. Yep.
Yeah, just a second. We have some technical troubles. Yeah. Let's see. Yeah, now we're back. Yes. Yeah. Yeah. So let's just use NumPy functions there, and let's see if it works better. Spoiler alert: it won't. So I will actually reduce the number over here to million, because. Oh, actually, well, let's go with the 10 millimeter, the same. But it won't make it faster. And like, you might think that, hey, what's the problem? Like wasn't NumPy supposed to make this, like, be this fast thing that makes stuff faster?
NumPy is
and
fast,
yeah,
but it is fast if you've got arrays and you're calculating on arrays. So can we do
so now we are.
this in an array fashion?
Yeah, so now we are at the point where, like, okay, we have figured out what is the problematic part, and the problematic part are the function calls. We have so many function calls, and now we have sought out and discovered like what is the problem, and now we can try to remedy that problem by doing what Susa exactly said, like making it into an array fashion. So instead of having this long list of like numbers, like for doing this for loop across all of these numbers, we can just get rid of the for loop and then just let NumPy give us lots of random numbers. So now we create like a lot of random numbers with one function call. And then we can do the same radius calculation we can do again. And now for the hits, like how do we actually calculate the hits? Well, we can check where the value r is less than 1. We can check where it's less than 1. And we get an array of like true or false values. And we can check how many are these. So we can just modify this to be a sum of true or false. And then this is basically our code. So now it's vectorized code, and it's working in this array fashion. And now if we profile it, well, it's 0.3 seconds, so it's a lot faster. So this is like a good example of like we get rid of one for loop because we turn something into these big blocks of numbers that can be worked together. Okay, and as an ending thing, we can look at the scaling. So we were now using the C profile thing, but there was the sampling profile called scaling. And this is a very nice tool that gives you like line by line information of the stuff you're going to calculating. Let's take the original code, and then I will.
I mean, to me, the main pro of using Scalene over using something a bit more built-in is that you get memory and CPU and everything, and you get quite nice, a quite nice overview with just one run. So if you don't know
and it also,
where is the problem really, that's
it will instead of like previously we had to interpret the output to see where the function calls were being made. With scaling, we will get oh sorry, I forgot. We have to load scaling first. With scaling, we will get this this monitoring data, that looks a lot nicer. So in your output, you might get an error because there was like the version of the IPython was changed, so scaling version might be a bit outdated. I have already made like a pull request upstream to Scale and developers that they should update the versions. But you can view the output also with this profile HTML if you can't see it in the Jupyter. If you want to try this out yourself and you can't see it in the Jupyter interface, you can also view the output in this HTML format. And if you're viewing it with this HTML format, you need to click this Trust HTML. And what you will see is this sort of an output. So what scaling provides, it provides you a report of the whole code, and it will show where time was used, and it will like show you that these lines were using most of the time, and this was the part that used most of the time, and you can straight up like look at various things over here. It can do memory profiling and GPU profiling and all sorts of stuff. But I think this is like a good place to stop. Like try this out, and usually these tools work best if you have some pieces of code that are like a function or whatever that you can independently measure, but sometimes you can also measure the whole program and see what sort of output you get. So this is like a good way of checking that. But now I think it's time to switch over to Luca and Thomas about library ecosystem in Python.
Yep.
Yeah. Thanks for that overview of profiling. That can become quite useful. I think we need to check this. Yeah, okay, the screen share is working again. So after this small excursion in profiling, we will come to something that underlies, I would say, most, if not all, of our work in scientific computing, and that's essentially the library ecosystem. So all the libraries that we have been talking about, like SciPy, NumPy, Matplotlib, Xarray, Scalene, all of these things give Python this kind of potency to address so many different problems relatively effectively. Because if you need to implement all of the features that these libraries give us, we wouldn't start working. So one thing that we kind of have to keep in mind is, yeah, we can't do everything ourselves. You don't want to reinvent the wheel. You want to use tools that other people have generated, and also to some extent you have to at the same time trust that what they have built is useful. It's the same as in science, where, well, we have to somewhat trust that the published papers have solid science underlying them, because otherwise all we build and all we proceed from there, yeah, wouldn't work. And luckily it most of the time works. And it's the same in computation and in libraries, that yeah, most of the time it works. Sometimes there are things that don't work, and then you can file a bug report and be fine. So, but if we are talking about libraries, what is it in general? So libraries are collections of code used by a program. A package is something that is more Python specific. It's one part of a library. It's something that has been, or just the library itself, something that has been made easily installable and reusable within Python. It's sometimes interchanged, or yeah, used in the same way as the word library. And the packages are often published on repositories such as the Python package index or Conda, so that you can easily install them. And dependencies are, well, what these packages again depend on, what they need as underlying tech. So in the ecosystem that we are working in, this is one part of the Python ecosystem. We are mostly working with scientific Python things like NumPy, Matplotlib. And these are the most basic libraries that are underlying almost anything, any other library that we are working with, any data analysis library and so on. And there are these core numeric libraries, NumPy, SciPy, and a lot of different plotting libraries. We have talked about Vega Altair. There's plenty of different data analysis libraries and packages like Pandas, XArray, well, with one R to any Network X for networking analysis. And all of them have their specific target problems that they aim at solving. And you can't just, we can't go into details of all of them because there's just too many. And this list here is mostly for you to have a look at and see, okay, what of these things is something that I might be able to use. These are packages that have been used by one or another of the instructors in this course over time. So what's listed here is probably quite robust in what it is doing and quite useful. There are a lot of things that are listed here as well that have more to do in how we interact with Python, with how we build our Python programs. And that includes things like IPython, which is, well, essentially an interactive interpreter that's a little bit nicer than the Python interpreter itself. We have Jupyter, which we have been using here quite a lot because it makes it quite easy to start building your Python code. But there are other editors like Spider, Visual Studio Code, PyCharm, which all provide features and are popular in their respective communities. There are things like Binder where you can essentially set up a completely online work environment, which allows you to already have the environments set up and so on online, but sometimes with a bit of limited resources. But they are great to include or to add as a demonstration as a demonstration portal for scientific results, where you can just put it onto a binder and someone else can rerun the code without having to install anything on their machine. They just do it online and can rerun the things. And you don't have to actually build a lot of additional things there. You can give it an environment and the code and just run and just run on that. There are things like testing libraries, which can become very useful once you want to build something that is supposed to become a library. Where when you find that, okay, I've now coded these 40 different functionalities, and I would actually like to share them. I would like to make them available to others. And that's the point where you can think about, maybe it would be good to write a couple of tests whether the things actually do what I expect them to do, and whether you can kind of reliably also handle things that are not the expected inputs, that they are throwing nice error messages and so on. And also writing documentation. There's, for example, Sphinx, but there are plenty of other tools as well. These whole lecture notes, they are created with Sphinx, and yeah, I think that's a relatively simple way to get something into a nice form that can also be deployed on GitHub, for example. There are lots and lots of data format support things like Pillow, H5Py, and PyTables for for different, more complex data types that allow you to read, write files or large files or more complex structured files in an efficient way. There are libraries for parallelism and code speedup, like MPI, Number, joblib, just to name a few, or to make C extensions, because on tendency, for example, NumPy is based a lot on, well, we are actually running the code itself in C and not in Python, because it's a lot faster, and we are just providing an interface to the compiled C things. And Python makes it easy to do just that. There are machine learning and deep learning libraries like XGBoost, scikit-learn, or PyTorch and TensorFlow, or JAX that has become more popular recently. And all of these packages help you in not having to reinvent the wheel. They provide a lot of additional resources, a lot of additional information, and make life a lot easier. Luca, what's your take on this? What kind of packages do you think are kind of the most important things that you do use, or do you actually use them?
Yeah, I use a lot of packages. I like working wheels are the best wheels. So yeah, I mean, I would say like generic ones like matplotlib, I would mention for plotting, like pandas for data libraries for data management, and NumPy, of course, most people generic ones. Then I guess it gets like very field specific, like everyone has their important in my field. Thinking to my like background from my PhD, I would definitely highlight SymPy for symbolic computation. That's, I think, pretty close to my heart, but for a lot of people might not be relevant. So yeah, then generic ones like plotting, data managing, they're probably the more field agnostics. What's your favorite?
Personally, I'm actually using something not in the scientific programming range at all, which is Fast API for web development, which makes it extremely simple to write a small web server that can very simply be spun up and provide data that could, for example, be an endpoint that you just provide that can run your code and allows other people to use what you have developed. Something that comes from my times back in science was CobraPy, which is constraint-based analysis, reconstruction analysis, which is a library that is quite popular in that field. But yeah, there are. I think the most important bit here is that there are very, very, very many packages around, and if you have a specific problem, have a look around. Maybe it's already solved. And when looking around, check if the libraries and things are actually what they say they are. Because especially recently, it has become more and more common that due to AI inventing packages, people have started to essentially try to inject wrong package names into source into things like Stack Overflow, and the AIs are starting to spew out package names that don't exist and essentially are viruses. And those then having been loaded onto PyPy with something that sounds roughly right, and the AI being happy with just saying, yeah, this is how it works, and yeah, that has or is becoming more and more of a problem. Also, typos, especially with AI-generated code. Be careful that the packages that are suggested and that it tells you to install are actually the packages. check the PyPy pages for it. Look around whether it's actually something that has been in use, and particularly for very recent things, yeah, be sure that it actually is a proper package and not something that was just spun up to inject stuff, because it's unfortunately happening nowadays. Yeah,
Another
so
thing I would add about libraries is that it's good, maybe it's often like overthought, overseen, but a lot of the popular open source libraries, they're not backed by like some corporate with people hired to develop it. A lot of popular libraries start with like some person doing it for fun and others finding it useful. So if you find an issue with the library and open an issue, remember to be nice. Remember it's probably someone who is doing that on their free times, and don't assume someone is like there's like money and people paid to fix the issues, because a lot of the cool libraries start as hobby projects from people kind enough to share. So I think that's often a very overseen side of libraries that people take for granted.
Yeah, I would agree. At the same time, I would say if you find bugs in libraries, most people are happy if bug reports are being written. It might take a bit of time for them to be corrected, and the optimal bit is if you understand the library well enough to actually be able to provide a bug fix. And yeah, it's the whole ecosystem here is something that is based on a two-way method. You are the users, but at the same time, you are also probably the people who can correct things that are wrong, and are the ones that, most likely figure out that this is not correct. And especially if it's a package that's very field specific, you will be the people who have, in the end, most knowledge about whether this is correct or not. It's this, don't use tools that have been established. For things that have not yet been kind of established, check them, try them out, see if they do what they claim to do. And if possible, walk a bit through the code to see if this is actually useful or if this is very strange. And it's also having a look into code is quite often a reasonable approach to say whether this is something that I want to use. Because if the code is so bad that I'm starting to read it and then say, no, I don't get anything here, I might not want to use this code, because if I can't at least understand the general concept, is that even trustworthy that this is actually producing what it's supposed to produce? And yeah, essentially every project can be turned into something that can be reused, as long as it's reproducible and relatively well created. Well maintained would be optimal, but if it's at least well created, this can even be some code that was just published once. If it's solid, there might need to be some updates if Python really changes enough that the code doesn't work anymore. But Python is, in contrast to a lot of other languages, very robust when it comes to backwards compatibility. So old code will normally run, as long as it doesn't rely on too many additional libraries, because those might not be backward compatible. But the base Python libraries, they are quite good there. So I think it would be interesting to see, maybe you could just start writing down a bit what kind of libraries you are using in your work, because that is something that other people can make use of as well. And we can talk a bit more about what we think is good here. Let's put this here. It's not a break. So yeah, if you could just write down in the collaborative document what kind of libraries you are using, that might help extending this page at some point, and or it might help others to see what is around, what can be used, what is useful. And if you could, for each library that you're using, that's not yet on the list, write a little bit, maybe a couple of words, what the library does. I think that would be really, really useful for others to see, okay, oh, I'm in a similar field, and I should have a look at this. It's something that I often notice and listening to these kind of software talks, that oh, okay, I never actually heard of that library. Huh? Maybe I should have a look. So, Luca, do you have anything else that you want to say here, or considerations when using when using a library, what to look for, what to check before just adopting, and running it?
Yeah, like I can mention like what I generally look at if I need to start a new library. Like I try not to give like too much weight of like who wrote that. Like in some open source communities are relatively small and everyone knows everyone, so but it can serve a bit of a bias. I try not to pay attention to that, but like how well it's maintained, like when was like a recent most time it was updated, like is it still actively maintained, developed? Although I will mention this sometimes a bit tricky because for some, there are like stable algorithms that have been developed in the 70s and never needed any update. So if something is working, why changing it? So that's also like something I would mention. Like don't say, hey, this hasn't been updated in like 10 years, so it's not working anymore. Well, the algorithm implemented hasn't been updated in 100 years. So what would you even update there? So that's
I would add to that. It's are there issues that are open and are not addressed in some way?
Yeah.
That's the more important bit to me, at least. Because yeah, I completely agree. Not updating, if there isn't anything to update, why update? So why change a running system? But if there are a bunch of issues that are not addressed or not interacted with at all, that's more a sign that okay, and but at the same time, I would also say it also depends a lot on the issues themselves. So
yeah, I agree.
don't just say, oh, there are 50 open issues. Yeah, maybe not. And because I have seen issues where I was like, okay, I could close this now because it's completely irrelevant, but I'm not entirely, but it feels wrong to just close it. So there are oftentimes things where issues stay open, because yeah, this would be a nice feature to have, but it's there's no one doing that feature. There's no one who has the time to do it, and that's not something that speaks against the library, because that's additional functionality that isn't yet implemented. And if it's exactly the feature that you need, then okay, maybe this is not the library, or alternatively, you could implement that and actually close the issue with your pull request.
Yeah, that's the beauty of open source. You can just do it. You don't need permission.
That would be the optimal solution. If the library is otherwise something where you think, okay, well, this is actually really useful to me. Yeah, so what do we have in the collaborative document now? Let's see. We have a lot of NumPy pandas. DuckDB is mentioned here, and yeah, DuckDB is quite useful as a data library for big data analysis, without well, at a stage where you don't yet want to install your own database servers. There DuckDB becomes really useful. Click is an alternative for outpowers. Is definitely more powerful, but is its own library is another dependency. So if you want to have a really nice interface or command line interface at least, yeah, click is definitely nice. If you want to have something basic, I would personally probably stick with argparse. We have PyTorch here, which is probably still the most popular library for any GPU machine learning, deep learning, machine learning model training approach. I personally would, also maybe add VLLM, which is a hosting library for large language models, which can become. It's a very simple way to just run a model. If you want to test specific models. Yeah, we have MNE or MNE Python for EEG and general neurobiology analysis. What else? I think I have to look at Signuc. Because additional workflow management. I know a bit of SnakeMake, but well, let's see if that could become interesting. I'm wondering whether the Python call.jl comes from my co-teacher.
Not me. Yeah, guilty.
Yeah.
Okay, so we have a couple of minutes left in the day. There is a feedback section for day 2 at the end. I would be very grateful if you can fill in your feedback about today. So just as a reminder, we covered plotting in the morning and data management. And then now in the afternoon, we've covered scripting, profiling, and then this section, selected libraries. So those are the sections, I guess, that the feedback would be about. But I mean, feel free to write in anything also about yesterday. Then tomorrow we'll go into, first of all, more high-performance computing kind of stuff, parallel programming, and integrating C code into Python with Cython in the morning. And then in the afternoon, we'll talk about how you can make your own Python packages from your code, so how you can make it installable easily on other systems, and how to manage dependencies.
Add your code to this list.
Yeah, add your code to the list, right? Yeah, so it will be an interesting day. It will definitely go a bit into slightly more advanced topics. I see that people think today's speed was better. Yesterday it was a bit fast, I have to admit. And today there's more votes on write speed, which is nice. But yeah, also it's nice to get good feedback, but it's also important to get to know what actually what we can improve, right? So that we can do better next time. So yeah, thanks to everyone for participating, and thanks for the feedback. I hope it was a useful day.
See you potentially tomorrow then.
Yeah.
Hopefully tomorrow.
Yeah, we'll see if anyone else pops up in the last 30 seconds or not. I don't think I've actually introduced myself at any point. Hey, I'm Jarno. I guess you can see my name there. I was subbing in for Enrico yesterday for a few seconds, and today I'm doing the outro. So otherwise, I've been in the background all the time. Yeah.
Jarno is one of the people who keep this whole thing running and making sure that we are actually going into breaks, having the notes up and so on, and not messing up too much.
But well, all right. Again, thanks for the feedback, and see you tomorrow.
See you tomorrow.
Bye. So usually we are still live, actually. The sound from instructors is still on. Hello, you can still hear me maybe? So if you click break, it will turn off the sound. That's what I always